Alright guys, check it out. Number 61, we're given the mass of a car. We're also given the time it takes to complete one lap. And notice how I used a capital T for this variable. I usually use lowercase t for time, but that's just for regular old any sort of time. If I have the time to complete exactly one lap, exactly one cycle, I'm going to use capital T to signify that that is the period. We're also given the radius, 50 meters. We need to find the acceleration of the car. Well, we're talking about going around in a circle, so we're talking about centripetal acceleration. Here is my equation for centripetal acceleration, and I have everything that I need to figure out exactly what it is. Next I need to find the force. So I know that F is equal to ma, and that works for any type of acceleration. So if you're talking about the acceleration of gravity, the force would be mass times the acceleration of gravity. If we're talking about acceleration centripetal, then the force centripetal is equal to mass times acceleration centripetal, as long as your F and your A are the same thing. So if you're talking about force of gravity, you need to use acceleration of gravity. If you're talking about the force centripetal, you need to use the centripetal acceleration. As long as they're the same, then you can use F equals ma. So we know the mass, so we can go ahead and solve for the centripetal force. Number 63, we're given a weird piece of information here. We're given revolutions per minute. But we don't want that. There's nothing we can do with revolutions per minute. We need the period. We need to know how long it takes for the coin to go around the turntable one time. That's what the period is. So how can we extrapolate the time for one revolution? We can use our factor label method. We know that one revolution, we want one revolution. We know that in a minute we can go 33 1/3 revolutions.
Miss Hackle, if you're still in the building, can you call 117?
Alright, sorry, the people came on the intercom. Let me see if I can back this up a little bit. Okay, we need to know the period, which is the time for one revolution. So that's what I wrote first. I want one revolution. And then I wrote down the conversion factor that we're provided. We're provided that in 1 minute we can go 33 1/3 revolutions, so now my revolutions cancel out. But I want the time in seconds, so then I converted minutes to seconds by multiplying by 60. So at the end of the day, we know it takes 1.8 seconds to do one revolution. So let's write that down at the top. 1.8 seconds is my period, capital T. Alright, so what are we trying to find out? The direction of acceleration. The direction of centripetal acceleration is always directed towards the center of your circle. In this case, it's a turntable. So the centripetal acceleration is directed towards the center of the record, or of the turntable, or whatever your circle is. Okay? Part B, we need to find the magnitude of the acceleration. Take a look at the equation for centripetal acceleration. 4 pi squared r divided by t squared. We've already found the period, so we know what our t is. The r is provided for you in the problem. 5 centimeters, 10 centimeters, 15 centimeters. Don't forget to convert that to meters before you plug it in. So you can find the centripetal acceleration for those three instances. I'm not going to do it for you. Part C, what force is acting on the coin? Well, let's think about it. This is a coin sitting on a record player. If there was no friction, if your record was made out of ice, what would happen? Well, the coin would fly off. As soon as you started the record player, if your record was made of ice, your coin would just fly off the edge and land on the floor. So, what force is keeping it on there? It must be friction. So you can use this sort of negative thinking to get you there. If there were no friction, the coin would fly off. So the force that's keeping it on there must be friction. Now I'll let you think about part D on your own. Where would the coin be most likely to fly off? You're going to have to look at your values for letter B to figure that out. 65, we're given the radius of a track, we're given the coefficient of friction. I want to quickly remind you what happens here when a car goes around a track. The car wants to keep on going straight. If you were driving on ice, your car would just go straight, just like that, and it would not make the turn. So why does it make the turn? What force allows your car to stay in that curve, to turn left? Well, we can use our negative thinking again. If it was ice, you would not be able to turn, you would just go straight. So, what allows you to turn is the force of friction. Friction is what allows you to turn when you're driving on the road. So how can we use that to solve this problem? Well, if friction is what allows us to turn, is what causes that force towards the center, we also know that that's called the centripetal force. So we can say that the force of friction is equal to the centripetal force. So let's write out both of our formulas here. The centripetal force is going to be mass times the centripetal acceleration. That's just your old school F equals ma. The force of friction is equal to mu mg, we know that. Take a look at the masses. The masses are going to cancel out. So then we have acceleration centripetal equals mu times g. We know the formula for centripetal acceleration, v squared over r, equals mu g. Watch how I rearrange this equation. And now I've arrived at a formula that will give me the value of v. I'm not going to do it for you. Alright, let's take a look at, 67. We have the mass of a pilot, and we're doing a loop-the-loop in our airplane. We're given the velocity. And it says that as the pilot's upside down, he experiences no force. So think about what that really means. If the pilot feels no force at the top of his loop when he's upside down, what that really means is that the sum of the forces are equal to 0. In other words, the forces are balanced. So what forces are we balancing anyway? Well, the force pulling him down is the force of gravity. The force pushing him into his seat is the centripetal force. So really what we're saying is that the centripetal force is equal to the force of gravity at that instant, at the top of his loop. The force pulling him down is equal to the force pushing him into his seat. That's why he doesn't feel anything. So if centripetal force is equal to force of gravity, we can set those two equations equal to one another. We know that the centripetal force is equal to mass times centripetal acceleration. On the right side of the equation, we know the force of gravity is equal to mass times g. Again, the masses cancel out. If you want to, you can put in 75. By all means, if you feel like it, you can go ahead and throw 75 in there, but they cancel out, so you don't have to. It's unnecessary. So now we can plug in our formula for centripetal acceleration. Let's rearrange it. Multiply both sides by r, divide by g. So now we have a definition for the radius. Radius equals v squared divided by g. So you can plug in your values there and find the radius. I hope that this was helpful.